Welcome to the wireless module of the Networking Fundamentals for Industrial Control Systems course. This module introduces you to the concepts and characteristics of routing and data delivery in an IP network. As a network operator, understanding these concepts to facilitate day-to-day operation and troubleshooting tasks is important. After you complete this module, you will be able to explain the radio frequency environment and attributes, as well as wireless network uses and topologies. Explore the concept of the wireless WAN technologies as an alternate mode of network access to include the variety of wireless transmission systems such as Wi-Fi, cellular, microwave, and satellite, and present a high-level overview of the concepts of wireless LANs, wireless mesh, RF planning, and basic wireless security. In this lesson, you will be introduced to the concept of wireless networking and the RF environment, RF attributes, and licensing agencies, as well as wireless usage and topologies. Radio frequency waves are used in communications such as radio, televisions, cordless phones, satellite communications, cellular phone service, and wireless LANs. RF is around everyone and everything and comes in many forms. RF energy is emitted from the numerous devices that use the energy for various types of communications. RF signals start with a high-frequency AC passing over a copper cable that is connected to antennas. These antennas will then transform the received electrical signal into radio waves that transmit through the air. A basic understanding of some of the concepts of physics as they relate to RF is important for any wireless networking professional. Radio transmission consists of two components, a transmitter and receiver. With IEEE 802.11 wireless networking, a wireless station can transmit and receive and is known as a transceiver. These two components work together. For every radio transmitter, there must be one or more radio receivers. Understanding the basic characteristics of RF transmissions is important. These characteristics work together to form AC signals and include the wavelength, frequency, amplitude, and phase. The antenna will transform these signals into radio waves that travel through the air, carrying information from the transmitter to the receiver. In a wireless LAN, the transmitter and receiver are typically the access point and client devices. In a wireless MAN, these devices may include a smartphone and a cell tower. In the wireless WAN, these components could be satellite and ground stations, or satellite dishes, or microwave antennas that are placed on towers or buildings for line-of-sight communications. RFs are radiated into the air by antennas that create radio waves. When radio waves are propagated through objects, they may be absorbed, for instance, by walls, or reflected, for instance, by metal surfaces. This absorption and reflection may cause areas of low signal strength or low signal quality. The following factors influence the transmission of radio waves. Reflection occurs when RF waves bounce off objects, for example, metal or glass surfaces. Scattering occurs when RF waves strike an uneven surface, for example, a rough surface, and are reflected in many directions. And absorption occurs when objects absorb RF waves, for example, walls. The following rules apply for data transmission over radio waves. Higher data rates have a shorter range because the receiver receives a stronger signal with a better signal-to-noise ratio, or SNR, to retrieve the information. Higher transmit power results in a greater range. The power has to increase by a factor of 4 to double the range. Higher data rates require more bandwidth. Increased bandwidth is possible with higher frequencies or more complex modulation. And higher frequencies have a shorter transmission range because they have higher degradation and absorption. This problem can be addressed by using more efficient antennas. Regulatory agencies control the use of the RF bands. New transmissions, modulations, and frequencies must be approved by regulatory agencies. A worldwide consistency is required. Regulatory agencies include the FCC for the United States, the European Telecommunications Standards Institute, or ETSI, for Europe, and the International Telecommunications Union, ITU, as a global organization for standardization. The Institute of Electrical and Electronic Engineers, IEEE, defines standards. IEEE 802.11 is part of the 802 networking standardization process. IEEE 802.11 is a group of standards for WLAN computer communication in the 2.4, 3.6, and 5 GHz frequency bands. The Wi-Fi Alliance offers certification for coordination between vendors of 802.11 products. Wi-Fi certification includes all three 802.11 RF technologies and Wi-Fi Protected Access, or WPA. The Wi-Fi Alliance promotes and influences WLAN standards. The ITU, FCC, and the IEEE have been instrumental in defining standards for the cellular telephone system, also referred to as the mobile network. The FCC and ITU govern the use of satellite and microwave systems. Wireless networks utilize a combination of licensed and unlicensed frequencies. Some common unlicensed bands in the United States are 2.4 GHz, used by Wi-Fi and Bluetooth technologies, 5 GHz, made popular by 802.11a, 24 GHz, wireless backhaul, and 60 GHz and up, 802.11ad draft specifications, also commonly found in proximity sensors in newer vehicles. In general, unlicensed devices usually do not get the higher power privileges licensed users get. Unlicensed users must also accept harmful interference from licensed users or other unlicensed users in the same space when the frequency band shares licensed and unlicensed parties. Mobile networks utilize frequencies that are centered in the UHF band. The UHF band is considered a niche for mobile networks because UHF frequencies can travel significant distances and easily penetrate objects. In this particular frequency range, there is a good balance between the range that can be achieved and the bandwidth that can be realized. In RF systems, the higher the frequency of the signal, the greater the bandwidth capability of the transmission. However, as the frequency of the signal increases, the range decreases. The longer the range, the lower the amount of available bandwidth. The shorter the range, the more bandwidth available. The cellular service utilizes different frequencies for different parts of the service. Some are used for voice, some are used for data, and others for both voice and data services. Both microwave and satellite transmissions take place in the 3 to 30 GHz frequency range technologies. However, unlike Wi-Fi, these technologies operate in narrow frequency bands that are strictly licensed and controlled by the FCC and the ITU. These technologies are also used for voice and data as well as network backhaul systems. Wireless communication in general refers to the means by which information is exchanged using RF signals. However, there is a substantial difference between a citizen's band, CB relay, and a TV relay, even if both fit the definition of wireless communications. To organize wireless technologies into groups, different classifications of radio communications are used, depending on the distance that the communications must travel. The system creates logical ensembles. Usage depends on distance. A 5-foot or 150 centimeters range is probably used for person-to-person communications, while a 150-mile or 240-kilometer range is more likely to be used for network-to-network exchanges. As you can see, there are various different technologies that are used for wireless communications. For example, wireless LANs, WLANs, provide robust wireless network connectivity over a local area of approximately 330 feet or 100 meters between an access point and associated clients. WLANs today are based on the 802.11 standard and are referred to as Wi-Fi networks. A wireless metropolitan area network, WMAN, is a wireless communications network that covers a large geographic area, such as a city or suburb. In this type of area, the wireless signal often provides a point-to-point or point-to-multipoint backbone. The IEEE has standardized a new set of WMAN technologies that operate in licensed and license-exempt frequency bands. The best known of these technologies is IEEE 802.16d or WiMAX, which is aimed at providing high-speed data access and voice IP services through the mobile network as opposed to providing just traditional cellular telephone connectivity. There are also other cellular technologies such as 4G, which are used in the WMAN wide metropolitan area networks and wireless WAN environment for access to data networks. These technologies have been developed to support high bandwidth data for the influx of mobile devices such as smartphones and tablets with web browsing and high bandwidth networking capabilities. This technology is also implemented for use with portable devices such as laptops. Also on the list are the traditional microwave and satellite technologies that are used for long-haul connectivity between network sites in the wireless WAN environment. In this lesson, you will be introduced to a variety of WAN RF technologies and the use of different wireless transmission systems to include Wi-Fi, cellular, microwave, and satellite. Some common wireless alternatives for network connectivity in the WAN environment include: microwave is frequently used for point-to-point connectivity between network sites within a metropolitan area where wide connectivity is unavailable or impractical. Microwave is also commonly used for long-haul connectivity and as a cellular backhaul system. Satellite systems are often used to provide connectivity between sites that are geographically dispersed across a very wide area. This process could mean multiple sites that need to be interconnected or sites that are quite distant from each other. Satellite is also used for rapidly deployed communications. Cellular systems are gaining importance as a technology for network connectivity due to advances in cellular data capability. Systems such as WiMAX and LTE are engineered to provide high bandwidth data connections. These connections are robust enough to support large file transfers to and from mobile devices as well as real-time voice and video for communications and video conferencing. Point-to-point microwave wireless backhaul systems are used to extend networks or manage devices in both cellular and broadband networks. Here, a microwave indoor unit is pictured below the outdoor unit. The indoor unit interfaces the radio with the network and the rest of the cell site. Microwave systems can be used to serve a number of different functions, from wireless Ethernet backhaul to site-to-site communications and connectivity in urban areas, as well as long-range point-to-point data and backhaul services. In networking, satellite systems are another technology using RF for communications. Satellite connections are best used when there is a requirement to achieve communications across a large geographic area and give some distinct advantages over traditional ground-based systems. These advantages include: satellite systems are adaptable to the needs of different customers because satellite systems can be deployed using various frequencies and bandwidths and can accommodate different types of data. For example, satellite systems are commonly used for video broadcasts. Satellite systems can be used when there is a requirement for mobility, especially across a large geographic area, and can offer significant cost advantages over building landlines for a limited population group. Due to very quick deployment capabilities, satellite systems are very cost-effective for short-term requirements like covering sporting events or news broadcasts. Satellite systems offer alternate routing or redundancy as required in the system through the deployment of more ground stations. They also offer great versatility in implementation for paging, voice, data, and video. Since satellites are based in orbit around the Earth, cost of bandwidth and use is independent of distance on the ground, making these systems especially attractive for long-haul communications. And with a satellite out in orbit over the Earth, there are no geographical obstructions that prohibit communications as there are with landlines. However, given the distance that the signal has to travel to reach the satellite and then return to a receiving station on the ground, transmission delay is always a significant drawback for satellite communications. Cellular communications are becoming increasingly important as an access technology to allow users remote access to corporate data networks or as a means of accessing those networks from non-traditional devices such as smartphones and tablets. The cellular network is now commonly used to transport voice, video, and data as opposed to the all-voice cellular phone networks of the past. Wireless in the WAN has also been adopted for use in the trucking industry by emergency response teams and police as well as other mobile network applications. Cellular communications can also be used as a WAN link for the network to pass data and access network services, as well as for general communications between network users such as texting and voice calls. Cellular can also be used as a WAN link alternate for connecting offices or network locations. Routers, just like tablets and cell phones, can connect to the cellular network using cell cards. Cellular networks have utilized a number of different RF technologies for connectivity and data transport. Each new RF technology utilizes allocated bands of the RF spectrum a little more efficiently to allow for higher, faster data rates, both upload and download. Here's a list of some of the current technologies. 3G or WiMAX allowed for more efficient use of the available spectrum to permit fast data transmission over the cellular network that is previously designed to support mostly voice communication. 4G or LTE permits even faster data transmission over the cellular network in support of high bandwidth applications such as streaming video in addition to file transfers and other type of data. Each evolutionary step in the cellular network leads towards supporting higher bandwidth for data transfers and data access in a mobile environment. In this lesson, you will be introduced to the concept of the wireless LAN as an alternate mode of access, the concepts of wireless mesh technology, and the roles of the wireless client, AP, and controller in a wireless LAN. You will also be presented with a high-level overview of the concepts of RF planning and AP placement, as well as the basic concepts of wireless security. A wireless LAN is a shared network very similar to a wired LAN. In a wireless LAN, an access point is a shared device that functions much like a shared Ethernet hub. In a wired network, the data is transmitted over some form of cabling to the shared hub. In a WLAN, data is transmitted using radio waves in frequency channels that are time-shared between users. Since the access point is a shared device, users must take turns transmitting user data just as if transmitting data through a wired LAN hub. Two-way radio communication, or half-duplex, is used. Unlike other wireless technologies, satellite systems for instance, in a wireless LAN, the same RF is used for transmitting and receiving or transceiving the data. In WLANs, RFs are used as the physical layer of the network. WLANs use a different frame format than wired Ethernet LANs. WLANs require additional information in the layer 2 header of the frame. Radio waves cause problems in WLANs that are not encountered in wired LANs. Connectivity issues occur in WLANs because of coverage problems, multipath distortion, and increased susceptibility to interference. If components are installed outdoors, changing environmental and weather conditions can cause interference. Privacy issues occur because RF can reach outside the facility. In WLANs, mobile clients connect to the network through an access point, which is the equivalent of a wired Ethernet hub, but an access point has some layer 2 features, making the access point have characteristics of switches. Mobile clients do not have a physical connection to the network. Mobile devices are often battery-powered as opposed to plugged-in LAN devices. WLANs must meet country-specific RF regulations. And the aim of standardization is to make WLANs available worldwide. Because WLANs use RF, they must follow country-specific regulations of RF power and frequencies. This requirement does not apply to LANs that are wired. The original IEEE 802.11 wireless standard was completed in June 1997. The standard was revised in 1999 to create IEEE 802.11a and 802.11b, then reaffirmed in 2003 as IEEE 802.11g, and reaffirmed again in 2009 as IEEE 802.11n, and again this year is 802.11ac. Remember that wireless uses half-duplex communication, so the basic throughput is only about half of the data rate. Because of this limitation, the IEEE 802.11b main development goal was to achieve higher data rates within the 2.4 GHz frequency band. The IEEE 802.11b standard defined the usage of newer encoding schemes to achieve higher data rates of 5.5 and 11 megabits per second while retaining a coding rate of 1 and 2 megabits per second. The same year that the 802.11b standard was adopted, IEEE developed another standard that is known as 802.11a. This standard motivates the goal of increasing data rates up to 54 megabits per second by using a different coding and modulation technology and using the less crowded frequency of 5 GHz. The 5 GHz band offered less interference for wireless LANs. Another development by IEEE obtained higher data rates. The IEEE 802.11g amendment uses the newer coding technology for higher speeds, yet is backward compatible with the 802.11b standard using the same 2.4 GHz frequency band. Data rates of 1, 2, 5.5, and 11 megabits per second are supported, as are data rates of 6, 9, 12, 18, 24, 36, 48, and 54 megabits per second. A more recent development by IEEE is the completed 802.11n standard as the upgrade to the 802.11 protocol. Using both the 2.4 GHz and 5 GHz frequency bands, IEEE 802.11n provides a new set of capabilities that dramatically improve the reliability of communications, the predictability of coverage, and the overall throughput of devices. 802.11ac, the emerging standard from the IEEE, is a faster and more scalable version of 802.11n. 802.11ac is a 5 GHz only technology and achieves its speed increase by bonding more channels for data transmission, denser modulation, and more multiple input and multiple output, whereas 802.11n stopped at 4 spatial streams. 802.11ac uses up to 8 spatial streams. So as you can see, the wireless LAN environment is an evolving one. There are two main modes of operation in a WLAN environment. There's the ad hoc mode. In this mode, wireless client devices connect to each other directly. Ad hoc mode does not involve the use of an access point to connect to the network. This type of connectivity is also referred to as Independent Basic Service Set, IBSS mode. And there is the infrastructure mode. This mode implements an access point as a control point for sharing wireless access to the wired network infrastructure. The AP functions as a translational bridge between 802.3 wired media and the 802.11 wireless media. The wireless connectivity is a half-duplex environment. A basic service area is a wireless cell, and the basic service set is the service that the AP provides. There are two implementations of infrastructure mode. Basic service set. In this implementation, mobile clients use a single access point for connecting to each other or to wired network resources. Extended service set. In this implementation, 2 or more BSSs connect by a common distribution system. The coverage area in which the AP and stations can communicate with each other is called a wireless cell or a basic service area. To communicate, a station must be able to detect the AP signal, and the AP must be able to detect the station's signal. Therefore, an AP exact coverage area might be different for each station, depending on each one's capabilities. The access point attaches to the Ethernet backbone and communicates with all of the wireless devices in the cell area. The access point is the master for the cell and controls traffic flow to and from the network. The remote devices do not communicate directly with each other. They communicate only with the access point. The access point is user configurable with its unique RF channel and wireless service set identifier name. All the devices within a given cell share the same medium, the air through which the radio signals travel, but only one signal can be transmitted at a time on the same channel, or collisions and data loss occur. When only one user is in a cell, that user has on-demand access to the medium. When many users are in a cell, they must compete for airtime, which means decreased network performance. To prevent loss of data due to simultaneous transmissions, the 802.11 standard dictates that all wireless communications be half-duplex. Only one end of the link may transmit or receive at a time. Further, the stations use carrier-sense multiple access with collision avoidance. Before a station can transmit data, the station must first listen to determine if another station is sending data. If no other station is transmitting, the station can begin sending its data. If another station is already transmitting data, however, the original station must wait the amount of time that is specified in the slot time parameter before trying to send a frame. The slot time is a parameter that you can configure on the AP. Although these guidelines allow devices to share the same medium, they limit the throughput of each. The SSID is used to logically separate WLANs and must match exactly between the client and the access point. The term WLAN is often used to define both the SSID and the associated parameters for the wireless interface, including such things as security settings and VLAN assignment. To maintain security, the network may require some kind of authorization to determine which client stations have the right to connect to the WLAN. For a client that is associated with a cell, the SSID identifies the WLAN that the client is associated with, as well as an area of coverage that is offered by the AP. The access point broadcasts the name of the wireless cell in the SSID by sending out a beacon signal. Beacons are broadcasts that access points send to announce the available services. The SSID identifies the WLAN and the basic service set that the client device associates with. However, clients can be configured without an SSID, called a null SSID, then detect all access points in the area and learn the SSID from the beacons of the access point. A common example of this discovery process is the one that uses the integrated wireless zero configuration utility when a wireless laptop is used at a new location. The user is shown a display of the newly found wireless service and asked to connect or supply appropriate keying material to join. SSID broadcast can be disabled on the access point, but this approach does not work if the client needs to see the SSID in the beacon. The AP associates a MAC address to the SSID. The name of the MAC address that is associated to an SSID is the Basic Service Set Identifier, or BSSID. The BSSID identifies the BSS and determines the AP coverage area. Because each AP in the network has a different radio MAC address, the derived MAC address is different on each AP for the same SSID name if multiple APs are configured to support the same service set. This SSID is a wireless workgroup name that is common to one or more APs that the client tries to associate with when moving from one cell to another within the wireless environment. If the client device is mobile, the device may move from the coverage area of one AP to the coverage area of another AP within the environment. When leaving the cell of one AP to access the network through a different AP, a common SSID pattern must signal this capability. This configuration allows a station that stays in an overlapping area to hear one SSID name and still understand that the SSID offers two APs. The association of a wireless client to a selected process point is actually the second step in a two-step process. First, the association process, then the authentication process must occur before an 802.11 client can pass traffic through the access point to another host on the network. In the client association process, the client scans all of the channels and listens for beacons and responses from the access points. During the association process, the SSID, MAC address, and security settings are sent from the client to the access point, and then the access point checks the settings, which later accepts or rejects the client. The client associates to the access point that has the strongest signal. If the signal becomes low, the client repeats the scan to associate with another access point. This process is called roaming. Client authentication in this initial process is not the same as network authentication. which is entering a username and password to gain access to the network. Client authentication is simply the first step, association follows, between the wireless client and access point and merely establishes connection. The 802.11 standard has specified two methods of authentication for a wireless client: open authentication and shared key authentication. Open authentication is simply the exchange of 4 hello-type packets without client or access point verification to allow ease of connectivity. Share key authentication uses a key that is known between the client and access point for verification. The same key may be used to encrypt the actual data passing between a wireless client and access point. Currently, there are many form factors available to add wireless capabilities to laptops if they do not have a Wi-Fi interface that is integrated as part of the system hardware. The most common are USB devices with self-contained fixed antennas and wireless supplement software. Both of them enable wireless hardware usage and provide security options for authentication and encryption. Most new laptops contain some form of wireless capability. The availability of wireless technology has increased the wireless market and improved ease of use. Newer Microsoft Windows operating systems have a basic wireless supplement client, that is WZC, to enable wireless plug-and-play. This functionality is performed by discovering SSIDs that are being broadcast and allowing the user to simply enter the matching security credentials or keys for WEP or WPA, for example. The basic features of WZC are satisfactory for simple small office or home office environments. Keep in mind that tablets and laptops generally have built-in wireless components as well, and rarely need an external Wi-Fi interface unless the interface is to allow them to use a newer wireless technology. Wireless network sizes can range from a single access point, or AP, to many thousands of APs covering a single campus. Wireless LANs, or WLANs, become difficult to manage as they grow in size if the configuration of APs is implemented only one at a time, as must be the case with autonomous APs. And these configurations need to be coordinated in order to provide a homogeneous service in terms of RF coverage, mobility, and security. When implementing a large wireless network with a great many access points to configure, implementing a wireless LAN controller for centralized management and monitoring of the wireless network environment in APs is beneficial. The Cisco Unified Wireless Networks architecture provides a way to centrally manage APs. The configuration of AP Service Set Identifier, or the SSID, power level, and channels can be automatically configured by a central control point. One of the biggest issues with implementing an IEEE 802.11 wireless network is the ability to monitor and maintain the network. Managing a wireless network implies configuring SSID and related parameters such as security, associated VLANs, and so on. Managing the channels and transmit power of APs to ensure optimal coverage, and managing roaming and transmission of client credentials from one AP to another so the connection will be maintained while the user moves. If the WLAN network comprises just a few APs, the administrator can configure each AP individually, reproducing similar configurations from one AP to another. Even with only a few APs, configuring the channel and exact transmit power of each AP can be challenging. In larger environments, the configuration of APs is more challenging. Changing an SSID parameter can involve the reconfiguration of hundreds of APs. The slightest difference in configuration details can create holes in the pattern of coverage. The Cisco Unified Wireless Network solution is based on a centrally controlled model. The Cisco WLAN controllers, or WLCs, are the central points of administration. The Cisco WLC controls and monitors the APs. Clients and APs send critical information back to the Cisco WLC regarding coverage, interference, and client data. Communication between the APs and the Cisco WLCs is provided through the control and provisioning of Wireless Access Points Protocol, or CAP-WAP. CAP-WAP is used to exchange control information between the APs and the Cisco WLC over an encrypted tunnel. Data information is also encapsulated in CAP-WAP, but not necessarily encrypted, and then the Cisco WLC will inject that data into the wired infrastructure onto the appropriate VLAN. This model provides improved control over security and traffic conditioning. A single Cisco WLC can manage many APs, however capacity is increased with additional Cisco WLCs. Real-time RF management is the key to the controller-based wireless solution. The Cisco WLAN controller uses dynamic algorithms and performs the following functions: radio resource monitoring, dynamic channel assignment, interference detection and avoidance, dynamic transmit power control, coverage hole detection and correction, and client and network load balancing. The controller-based solution makes configuring the support of multiple wireless LANs by a group of access points easier. Multiple APs connected to a given controller will support each WLAN, but also other APs managed by different controllers belonging to the same mobility group. A mobility group is a set of controllers cooperating to offer users the possibility to move seamlessly across a domain where controllers managing different APs offer this service. This process allows users to roam without having to interrupt their session to authenticate again. Each WLAN may have a respective security requirement and a specific method of authentication. Again, this being managed centrally from the controller makes the WLAN more easily to control and manage. Each WLAN will attach users to the enterprise network by associating them with a specific VLAN from where an IP address can be derived through DHCP based on the WLAN to VLAN association, which is defined at controller level, thus avoiding complex cross-configuration of multiple individual autonomous APs. Dynamic balancing is a direct benefit of the controller-based approach in the way that global RF and client management becomes easier when dynamic balancing is done from a single vantage point, the Cisco WLC, from where a large collection of APs is seen and managed. While wireless networks have become integral to many enterprises seeking to optimize productivity, providing full wireless coverage remains a challenge in a number of environments. To provide pervasive network connectivity, enterprises must be able to deploy wireless access points wherever necessary, often above ceilings or across millions of square feet, indoor or outdoor. Running Ethernet cable to every access point required to provide full coverage is often too difficult in hard-to-wire environments, from warehouses with expansive spaces to historic buildings requiring special care or city streets. Originally developed for outdoor wireless backhaul, mesh technology now provides flexible, comprehensive wireless coverage with the same reach and scalability for outdoor and indoor environments. The Cisco wireless mesh networking solution provides wireless connectivity to areas that until now have been difficult or impossible to wire. Most Cisco access points can be enabled to a mesh mode based on intelligent wireless routing technology and a powerful self-organizing, self-healing, and self-configuring architecture. The Cisco wireless mesh networking solution is simple to deploy and manage while offering comprehensive coverage and optimal network performance to a wide variety of environments. Mesh networking infrastructure is decentralized and relatively inexpensive, as each node or AP need only to transmit as far as the next AP. APs act as repeaters to transmit data from nearby APs to peers that are too far away for a manageable cabled connection, so the network can span a large distance, especially over rough or difficult terrain. Mesh networks are also reliable as each AP can potentially connect to one of several other neighbor APs. The networks are self-healing in that if one AP drops out of the network due to hardware failure or any other reason, that AP neighbors simply provide another route, thus reducing network outages and management costs. Beyond redundancy, extra capacity can be installed by adding more APs. Wireless mesh connections between AP nodes are formed with a radio link. This connection allows many possible paths from a given node to other nodes. Paths through the mesh network can change in response to traffic loads, radio conditions, or traffic prioritization. Wireless mesh networks differ from other wireless networks in that only subsets of the nodes need to be connected to the wired network. The network can cover more distance by using nodes that are not connected to the wired network. Access points operating in wireless mesh mode use the Adaptive Wireless Path Protocol (AWPP) to establish dynamic wireless connections to their neighboring access points. Using one radio, each access point can then provide wireless coverage for client devices within the access point area, while backhauling traffic through the second radio. Because AWPP dynamically learns the best way to route traffic wirelessly across multiple hops back to the wired network, the AWPP ensures maximum network availability. The entire mesh architecture is designed to allow for easily adding APs and controllers to increase coverage and capacity. The AWPP will allow the network to self-heal and incorporate the new APs and controllers seamlessly. The Cisco architecture is designed with the capacity for multiple wireless hops back to the wired network. However, optimal performance is provided when the wireless hop count is at 3 to 4 hops. The AP in the mesh network providing access to the wired network is called the root AP or RAP. The other APs in the mesh network are called mesh APs or MAP. Quality of service, or QoS, is supported to allow traffic rate limiting to prevent traffic hogs. Multiple WLANs allow providers to segment based on user type. When implementing a wireless network, you must consider both coverage and capacity. Coverage refers to providing the wireless signal where coverage is needed. Likewise, you must identify areas where the company does not want the wireless signal to go and try to avoid allowing the signal to leak into those areas. Likewise, you must identify areas where the company does not want the wireless signal to go and try to avoid allowing the signal to leak into those areas. For example, a signal leaking into adjacent office spaces belonging to another company in a shared building or out into a parking lot. Capacity refers to the cell ability to carry a data load, cell throughput. In other words, how much data can the cell reliably support at the configured powers and the speeds of the cell devices. As long as device configurations do not change and there is no change in the physical environment to create interference, cell capacity does not change. Overall throughput remains the same in the more densely occupied cell as in the less crowded one. However, the per-user throughput decreases as more stations join the cell. As the capacity ceiling is approached, users will begin to notice decreased speed and reliability. User density is perhaps the most obvious and easily controlled element that affects capacity. If more users occupy a cell, more bit streams are in the air or in buffers competing for limited resources. You must consider many factors when calculating coverage and capacity. Transmit power and receiver sensitivity. The transmit power is the strength of the signal output by the transmitting radio, and the receiver sensitivity is the ability of the receiver to detect the signal. These factors are the cornerstone determinants for coverage and range. Antennas on both the transmitter and the receiver boost the signal strength, allowing a larger area of coverage. The antenna pattern is also a critical element of the system design. Obstacles reflect and absorb radio waves and can create a dead space in the expected coverage area. Keep in mind that some environments might not be a static configuration. For example, a manufacturing floor could have large equipment moving, or a wafer factory might have concrete obstructions blocking line of sight demanding wireless repeaters. Average number of stations in the cell. In addition to calculating the throughput expected for the cell, you should estimate the throughput that an individual station can expect. Operating mode. The operating mode can affect capacity because 802.11n provides higher data rates than 802.11g or 802.11a, which both provide higher data rates than 802.11b. Together, these factors affect the areas where a wireless station can communicate successfully with the AP and, in effect, the coverage. In the case of a wireless mesh system, considering the amount of traffic being pushed through the wireless uplinks between APs versus the bandwidth from radios that are used for client access is also necessary. Asking the right questions is the key to any successful WLAN deployment. Each company and location has unique needs that must be taken into account. A site survey is a must for any wireless deployment involving more than one access point. The site survey is meant to get a precise view of the line of business, products, and services offered, and the reason for the wireless network implementation, as well as the type of building in which wireless deployment might be needed. You need to assess the size of the client, population, and what level of performance they require. Clearly identify the coverage areas, as well as how much mobility of people with their devices must be allowed. A walkthrough that is aimed at assessing follows the first customer meeting and the type of environment to cover in their facility. This step is very important to set the customer expectations and avoid surprises. If the area to cover is outdoors, the initial walkthrough will allow you to identify possible problematic areas. You may be able to connect some of the APs to LAN switches and have sources of power within range. On the other hand, if the area to cover is far from any building, power and wired connections will be an issue, which will affect AP location and throughput. You will then consider a mesh deployment. Indoors, covering an office building is not the same as covering a warehouse. You will then want to identify more densely populated areas, groups of power users, potential RF obstacles, and any other constraints or possible sources of limitations. Security requirements, such as protecting confidential information by confining the information inside specific coverage areas, will also influence the design of the network. Finally, reaching a formal agreement with the customer on the results of this survey by having a formal sign-off process is essential. However, this process must not preclude any review of this survey should any important change in the company environment take place. Tools are available which will allow the computation of the appropriate number and type of APs required to provide the services, coverage, and performance that is identified during the site survey. To generate a proposal, a user enters the expected wireless client user density and services to support such as data, voice, and location. Based on the throughput that is specified for each AP radio, the planning tool calculates the total number of access points that are required to provide optimum coverage in the network. You can calculate the recommended number and location of access points that are based on the following criteria: traffic type active on the network, including data, voice, traffic, or both; location accuracy requirements; number of active users; and number of users per square footage. This criteria will generate a map that shows the proposed deployment of the recommended access points in the selected area that is based on the selected services and parameters. This proposed set of APs can be edited, modified, and fine-tuned. The resulting RF propagation, coverage, and throughput can be improved by manual operation until the solution fits the requirements of the customer. A wireless networking proposal can be generated using the information that is gathered from the map and planning tool. The proposal will give information on how the planning was done and also prints out the heat map so that the coverage can be seen and verified. This map will also give you a good idea of where the RF signal is being propagated or not being propagated so that steps may be taken to secure the wireless environment from unwanted access. Given the nature of wireless systems sending RF signals out into the open airspace, systems vulnerable to attack is inevitable. Incidents have been reported of people using numerous open-source applications to collect and exploit vulnerabilities in the IEEE 802.11 standard security mechanism called Wired Equivalent Privacy, or WEP. Wireless sniffers enable network engineers to passively capture data packets so that they can be examined to correct system problems. These same sniffers can exploit known security weaknesses by hackers. War driving originally meant using a cellular scanning device to find cell phone numbers to exploit. War driving now also means driving around with a laptop and an 802.11b or G client card to find an 802.11b or G system to exploit. Most wireless devices that are sold today are WLAN ready. End users often do not change default settings, or they implement only standard web security, which is not optimal for securing wireless networks. With basic web encryption enabled, or obviously with no encryption enabled, collecting data and obtaining sensitive network information, such as user login information, account numbers, and personal records, is possible. A rogue access point is an unauthorized access point that is connected to the corporate network. If a rogue access point is programmed with the correct web key, client data could be captured. A rogue access point could also be configured to provide unauthorized users with information such as MAC addresses or clients, wireless and wired, or to capture and spoof data packets. At worst, a rogue access point could be configured to gain access to servers and files. A simple and common version of a rogue access point is one installed without authorization. Employee access points that are intended for home use and are configured without the necessary security can cause a security risk in the enterprise network. To secure a WLAN, the following steps are required. Authentication ensures that legitimate clients and users access the network via trusted access points. Encryption to provide privacy and confidentiality. Intrusion detection systems and intrusion prevention systems to protect from security risk and increase availability. There are also air monitor systems that monitor for system activity, hot zones, and vulnerabilities. The fundamental solution for wireless security is authentication and encryption to protect the wireless data transmission. These two wireless security solutions can be implemented in degrees. However, both apply to both small office, home office, and large enterprise wireless networks. Larger enterprise networks will need the additional security that an IPS monitor offers. Current IPSs can not only detect wireless network attacks, but they also provide basic protection against unauthorized clients and access points. Many enterprise networks use IPSs not only for protection against outside threats, but also to protect against unauthorized access through access points that employees install who desire the mobility and benefits of wireless. The following key points were discussed in this module. Wireless systems use various licensed and unlicensed radio frequencies to facilitate communication. These systems can be used for LAN, MAN, and WAN applications. Wireless technologies such as microwave, satellite, and cellular networks can provide an alternative to traditional wired WAN solutions for sites that are difficult to reach, need to be enabled quickly, or require mobility. WLANs can enable a mobile workforce in an office or campus environment, but require careful planning for coverage and security. The APs that the clients connect to can be deployed independently or using a wireless LAN controller for centralized management and monitoring of the environment. Wireless mesh technology now provides flexible, comprehensive wireless coverage with the same reach and scalability for outdoor and indoor environments. A site survey is a must for any wireless deployment involving more than one access point, because each implementation is unique, and asking the right questions is the key to any successful WLAN deployment. And the fundamental solution for wireless security is authentication and encryption to protect the wireless data transmission.